oxygen.
Yeah, I'm hearing a series of options here. So I'm hearing attack the proton on the alcohol, and also I'm hearing it attack here and kick bromine off, because bromine's a good leaving group. Let's carry out each one of these potential options. Now, bromine is a good leaving group, but now, is a lonely hydrogen going to be strong enough to kick bromine off of there? Nope. So we're not going to attack there. Even though we have a leaving group sitting there, we're not going to be able to attack there with H-. And for those of you who said it attacks the proton and alcohol, that's right. It's going to come over here and attack that proton off the alcohol instead. And what do we lose as a byproduct? H2 gas. So whenever you see NaH, you will always lose H2 gas, because it is going to react with another proton, and when it does so, flies off as that majestic H2 gas, which is explosive, actually, very explosive. It's the main component in rocket fuel. So, hey, very fun stuff to use. But right, we take that proton off of there and we get H2 gas. What happens to that oxygen?
He becomes negatively charged.
Negatively charged, right? Now that oxygen with a negative charge it's wanting something. It wants to attack something, right? What is it allowed to attack here?
Bromine.
Now we can attack up here and kick bromine off. You guys have seen this reaction done several times before. This is how we can create a cyclic ether. Basically an ether that is enclosed in a ring structure, which if I can get the right number of carbons in here, right? Double check our carbon number, 1, 2, 3, 4, 5, 1, 2, 3, 4, 5. We get a nice cyclic ether there. And then what happens here? We're adding excess hydrobromic acid. So what kind of mechanism is happening here?
SN2.
It's a nice SN2, but there's something special about this one.
Double SN2.
It's a double SN2. Double SN2 because we have a lonely oxygen here that's going to attack HBr 2 times, and we get 2 bromines that attach. So what I can do is redraw the ring structure. But now instead of having oxygen there, we now have a pair of bromines. I could obviously, stretch the chain out and make it linear, make it more stable, but that's our product right there. That excess bromic acid is going to simply get rid of this oxygen. And we're going to gradually replace it with sets of bromines. And you guys have seen this guy on your quiz before. Nothing too terribly complex there. And then we don't even need to bother with this guy. We know he's going to be an elimination, hands down. We've seen this molecule several times before. But okay. Any other questions on page 1, though? Anything there that's still not quite feeling up to snuff there?
For the reaction with the HBr, how do you know it happens twice?
So how do we know for this one, that the reaction happens twice? When we add well, the big hint here is the excess, but let's say we didn't know what that meant. Let's say that we didn't know that the excess actually meant anything for us. When we add a proton to this becomes what? Becomes OH plus, right? Because we have 2 bonds here. We break that bond, bromine comes in, takes its place. That's one substitution reaction there. But now what does the hydroxyl do once it breaks free? It takes something out of solution. It takes another proton. So it becomes what after that?
Water.
It becomes water, which then leaves and bromine takes its place a second time. So that's how we know this happens twice, is this oxygen has to basically become water at some point in order to fully leave. And without a proton already there, we have to supply one to get that first elimination or first substitution going. And again, the excess is a big hint here that it tells you it happens twice. As a rule of thumb, cyclic ethers will do double substitutions. So if you see a ring that's got an oxygen stuffed in the middle of it, you're probably going to do a double substitution with it somewhere along the way. Either with HBr, HCl, or even with with HI, idioic acid. But any other questions on the first page?
Can you explain the rotation of CN down?
For this one. So the question there was, how does CN right here end up rotating downward? So the big thing here is it technically isn't going to rotate, so to speak. It's just the way that we've drawn it. So now, when we carry out the elimination here, right? Bromine gets removed. We're taking this proton, right? Because it is what? What's that nice, sensual word?
Okay.
That anti-what? Anti-what?
Anti-paraplanar.
Oh yeah, that anti-paraplanar. Because that's the good stuff. That right there will tickle your giblets in the morning. That right there is what we're after. But now we drop this down here, and now we no longer have we don't have a stereo center there anymore. But there is something that we do know about these two cyanides before we actually draw our final product. Before this double bond got dropped here, where were they with respect to each other? Are they on opposite planes, the same plane?
Same.
They're on the same. Even though they're pointing in opposite directions, they're both wedged. So in our final answer, we can draw them both pointing down here, or we can draw them both pointing up here.
Oh.
And then the methyl has to, by default, point in the other direction. So the methyl here would be pointing up. Over here, it'd be pointing down. We could draw either one. So it's not really the cyanide rotating, so to speak. It just depends on how you draw the final product. You just have to make sure that the two cyanides are on the same side of the molecule, because before that double bond got dropped there, they were both pointing up into the air. We can't say they were both pointing up into the air, so we have to use the bond line, but they have to be on the same side of the molecule.
Does it matter where you put your methyl, like on the left or the right?
Ah, good question there. Does it matter where we actually draw the methyl? Technically, not really. We could put it on this side or this side. As long as there's just one methyl, that's all that matters. Any other questions on page 1? Any other questions on this stuff?
No.
Not too bad, right? Not too bad? All right, let's see if we got any problem children on page 2. Let's see. Oh my gosh. That very first one should be a dead giveaway. What are we using here?
Hydride.
I tried.
No, it's a two-step, so it's a lot.
Yep, so we're using a hydride, right? We're turning a ketone into an alcohol, but with a nice hydrogen there that's actually drawn for us. How nice. We know exactly what's going on here. But it's a two-stepper. Who's a two-step process out of the two hydrides?
Law water.
Law water. LAH and water. Yep, law water. Simple as that. Now, what if it had just one there? What if it's just a one-step mechanism?
Sodium borohydride.
It'd be sodium borohydride with what as a solvent?
Methanol.
Toss in some methanol. Yep, all in one step. And then, oh goodness gracious, alcohol, double bond. What the fudge happened here?
Elimination.
Elimination.
Yeah, so we can toss in some of that sweet H2SO4 and heat, and boom, there it is again. There's a pattern going here, right?
And we'd say it's E1.
Mm-hmm. We say this guy would be a nice E1. What do you guys notice about that synthesis problem? Every single step for that retrosynthesis problem can be found throughout the midterm.
Yay.
And that is done on purpose. That's why I also say to approach that one last, because as you go through the midterm, you're going to see examples of how to do every single step required for the retrosynthesis problem, regardless of what it is. So if you approach it first, you're like, okay, I have no idea where to start. If you go through the first 2 pages, you just might get an idea or two.
Hint, hint, wink, wink.
Yep, wink, wink, hint, hint, sniff, sniff, whatever happens, right? Oh, look, Grignard. Well, shoot.
How do you say that?
Oh, look, Grignard alcohol. Yay, I did it. Okay. We know this one. We know this one. We're strolling along. We're strolling along. Ah! What the hell is this?
What's it?
There's CO2 being added to this one. That's not a ketone. Is it an aldehyde?
No.
No, it's neither. What the hell?
WTF?
Sam, what the hell? It has to attack ketones or aldehydes. That's not either. Rage quit. Why? Now, I did point this out when I drew the generic structures for the ketone and the aldehyde. What do they have in common?
The carbon.
They've got the carbonyl, the C double bond O. What does this have?
C double bond. Oh.
It's got C double bond O, but twice over. So guess what? A Grignard will attack this the same way, even though it's not a ketone or aldehyde. If it's got the carbonyl in it, it can be attacked. And we're going to show here that it can be attacked. So we add our magnesium here. And this is going to come along, but I'm going to just stuff the magnesium in there because we know it attaches there. We make our nice little carbanion, and that's going to come here and attack this carbon. Now, does it matter where we push the electrons?
No.
Not really. We can push it up to the top one or the bottom. So we just redraw the carbon chain. Carbon. And now that guy's hanging off of there. Now Wagner is ridiculously polite because he's even asked you to draw this. What does he do in the answer key for this one?
CO2.
Yep, he's abbreviated as this. As CO2H. But I find it more helpful to draw the structure out so you guys can see how that guy is arranged, how that guy is bonded. And technically, we didn't make an alcohol there. What did we make? What kind of functional group is this?
Carboxylic acid.
Uh-huh, that's right. This front row knows there she is. That is a carboxylic acid. Now, we did get the alcohol. We did get the OH there. But that is part of a larger functional group, right, known as the carboxylic acid. And now, oh no, what's this? What's sodium hydride doing here? What are we losing?
So how are we going to leave losing the
Carbon? No.
So, what are we losing?
H2 gas?
I don't know.
We're losing that H2 gas, right. We lose that H2 gas. It makes this guy O minus. And then what is this going to do? This oxygen's going to attack that methyl. And then who's leaving? That iodine. So when we attack it with our, strengthened nucleophile, the double bond's still there, but now we have an oxygen, and what's hanging off of it? CH3. Now, who can tell me what kind of functional group that is? So that's a carboxylic acid on the left. What is this on the right? What is that?
Ester.
Starts with an E.
Ester.
Yep. As the crowd goes wild. Woo! That is an ester. Right. And that's it. That's all there is to it. This one is just tricky because of the CO2. Oh, wow. SCH3. Wow. It's as if I've never seen this before. What kind of mechanism is this?
It's a substitution.
Substitution. Nice SN2, right? I'm just going to redraw my molecule.
Yeah.
Hmm?
The one before that, for the double bond, the second product, is there oxygen attached to the carbon?
Ah, yeah, good question there. Yeah, is there an oxygen attached to that carbon?
Is there double bond on top? There's no oxygen there?
Yes. Yep, good question there. There is still a double bonded oxygen sitting up there in our final product because it didn't go anywhere. We took the proton off, this attacked the methyl, that double bond oxygen never went anywhere. So it will still be in our final product. Okay, good. I drew out my product.
Isn't Doesn't it change?
A lot of you guys are raising eyebrows at this one. What's wrong?